Here it is. We've reached the end of the optics session. This is lesson 30 from our no-nonsense A-level physics lesson series, all about the diffraction grating. So what is a diffraction grating? Well, what was a single slit and what are double slits? All they are glass plates where we've covered them in some sort of dye to make them opaque. Then we've etched out or scratched out a line. We've scratched out a line so that light can get through, and we can scratch it out of different thickness scratches, and we can scratch a single line to get a single slit, two lines to get double slit, or in this case, lots and lots and lots of slits. So this is going to be lots of slits. We could say an infinite number of slits, but let's just say lots of slits. I'm just going to choose the pen. Lots of slits that are close together. And usually what we are told is how many slits there are per millimeter. So you might have something like 300 slits per millimeter. Well, usually in A-level, of course, that would be written as slits millimeters to the -1. What would that be equal to? Well, that would be equal to 1 over 300 millimeters between each slit. And you could calculate what that is. We could have 600 slits per millimeter. Well, that's going to be a situation where we have 1 over 600 millimeters between each slit, and so on and so on. So we do need to be able to convert, because it is important to know the distance between slits for the diffraction grating equation. Now, first of all, what do diffraction gratings do? Well, they are going to split a single beam into lots of different beams, and it goes a little bit like this. If I have a source, perhaps it's a laser, I'll draw it up here, and I'll label it laser. So it's monochromatic, coherent, and I have my diffraction grating, which I'm going to do here, just like this. That is an awful lot of slits very close together. And I'll label that diffraction grating. Then what we're going to do is we are going to get a beam that, rather uninterestingly, goes straight through. But we're also going to get beams that come through at different angles, like this. And there's going to be a finite number of them. And we'll be able to count how many of these, what we call orders, there are, and how many spots we have. Now, this can be really useful. If we use light that's not monochromatic, then we're going to get different numbers of orders and different spacings between the orders for the different colors. So the order that goes straight through, we call the 0th order. I'm going to write this sideways on. Well, I'm going to try to. Oh, I've got the wrong pen selected, as I often do. The 0th order. We then have either side of that the 1st order, Star Wars fans are getting all excited now. Here we have the 2nd order, and so on. And so on, all the way around. So we've got 0th, 1st, 2nd, and so on. And the number of orders that we can go up to, in this case, it's 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4. Oh, I haven't drawn this very symmetrical, have I? 2, 3, 4, 0, 1, 2, 3, 4, 5. I should draw one extra order on the other side. It's not very symmetrical at all. There we go. Well, I made an effort. 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5. So we are going up to the 5th order on both sides. 5th, 5th. And there are 11 dots that would appear. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I'm counting them. So whatever the maximum order is, you double it and plus 1, and that is how many orders you get. So you get the maximum order times 2 plus 1 spots on a screen. And I'm using n here for the order. You can use m or n. I'm using n. So the maximum order, double it, plus 1, that's how many spots you get on the screen. Okay. And there are angles between these orders, and the angle between the orders we can calculate. So we're going to derive an equation. But first of all, let's try and understand the physics of what's going on. Because we've got an infinite number of orders, an infinite number of slits, try again, because we've got an infinite number of slits that are all being illuminated with this coherent monochromatic light, then there should be cancellation somewhere. Somewhere there'll be light that arrives and cancels out. Let me show you what I mean. Let's draw a bunch of slits. Let's just do a diagram. Using Huygens wavelets. So if I just draw a diagram, what we've got is a bunch of slits. So let's draw 1, 2, 3. In fact, what I'll do is I'll cheat. I'll draw one of them and then I'll rub out where the slits are, because I have the technology. I can do that sort of thing. So let's rub that one out, 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 let's rub that one out. So I've got a bunch of these. And if I look at any point somewhere, let's just take this point here and see what's happening. Well, we're going to have the light from this slit here traveling a certain distance. And there will be another slit somewhere where the light will interfere destructively. And I could have the light coming from here and the light coming from somewhere else where it will interfere destructively. Because there's an infinite number of slits, I'm going to be able to find one where we get destructive interference to match every other slit. So in a way, you'd think, well, there's going to be no light there at all. There can't be any light observed to the right-hand side at all. But imagine I've got incident wavefronts from the left-hand side, which are all evenly spaced. Okay, so let's do the best we can for this. I'm going to draw the first wavelet like this. I'm going to make it quite small. And this is going to emerge from there. That's going to be my wave length. About half the spacing between the slits as I've drawn it here. Oopsie, no, we don't want that. Let's undo that. And let's select this and let's pop this here. And I'm going to just draw all these little wavelets all the way down. We already know that if I look some distance away, that they are all going to line up the wavefronts, because we've seen that before to produce each subsequent wavefront by looking at the superposition of these wavelets. Right, now we're going to draw the next wavefront, and I'm going to use green for this, and let's make the, let's make them, it'd be better if I was on square paper, wouldn't it? But there we are, we're on lined paper, so we're going to make this work. So there's the next wave front from the first slit, from the second slit. This will all become clear in a bit. Do your best to draw this as carefully as you can. If it was easy, everyone would do it. And then we're going to do a third one. And I might even do a fourth and a fifth one. So we've done red, we've done green, let's do blue. And this is going to be the next time period later. So remember, each of these wavefronts, or these wavelets, is drawn one time period after the one before. So there it is. So the distance between adjacent wave fronts should be equal to, oopsie, not that one, should be equal to one wavelength. Oh, I've lost it. There's the diagram. I missed out that one. 1, 2, 3 I've done. 4 is this one here. You can label it all if it helps. Not really sure if it will. Let's drop that off there and so on. Let's do another one. So let's draw purple wavefront. Another time period later. Is that the one I've just done? No, I think that's right. They're supposed to be circular, and they're not perfectly circular, but you know, they're not bad, are they? I've seen worse diagrams. I've drawn worse diagrams. And this is going to look really, really confusing. It's really quite difficult to see what's going on, but all will make sense in a moment. Copy that there. Copy that there. Right, so you can see the various places where the wavefronts will all end up lining up. Just as we had before, we had, let's use the straight line tool, we had the red ones will line up at some position, then we'll have the green ones that will line up some position later. Then we'll have the blue ones that will line up some position after that. And then we'll have the purple ones that will line up at some position after that. And so on and so on and so on. So we'll get these wavefronts and I could draw them all going out like that. Right, that's fine. But that would produce the 0th order. What about the first order? But if I draw a line that connects the first wavefront, the second wavefront, to the third wavefront, to the fourth wavefront, so let's try and draw it right. First, second, third, fourth, like that. So where is it connecting to those wavefronts? Well, from the first slit, it's connected to the 0th wavefront. So this is slit number 1. From slit number 2, it's connected to the first wavefront. That's there. Slit number 3, it's connected to the second wavefront from slit number 3 there. Slit number 4, it's connected to the third wavefront, which is there. Slit number 5, it's connected to the fourth wavefront, which is that one there. So let's actually use some colors for this. So we've got slit, let's call this slit 0, because there's the 0th wavefront. Then we've got slit 1, which is this wavefront here. Then we've got slit 2, which is this wavefront, oops, here. Then we've got slit 3, which is this wavefront here. Oops. like that. And then we have slit 4 there, and it's this wavefront here. So you can see that they all line up as well. And each wavefront that we add, we are going to push that superposition wavefront one further away. So that is going to be the wavefront for the first order. And I'm going to label this the first order wavefront. So first order wavefront. We could do it again for the second order wavefront. So let's change to a different color. So instead of connecting from adding one wavefront for each slit, we're going to add 2 wavefronts for each slit. So we're starting here, and then in the second slit, we're going to connect. We're going to draw a line that passes through the not the red one, but the green one. Oh, that's going to be all the way down here. And then it'll have to pass through for the next one, not the blue one, but the purple one, which is, again, it's all the way down here. Well, the second wavefront's not very good because I've chosen too big a wavelength. If I chose a smaller wavelength, we'd be able to see more orders. I can do the same thing for each slit. So let's just go from this one here and connect to the first wavefront from the slit above it, second wavefront from the slit above it, third wavefront from the slit above it, and so on like this. I could do the same thing for this one. So first wavefront, second wavefront. Oh, I haven't drawn the third one because there's no slits above it. This one here goes through here, and so on. So I have all of these wavefronts where hopefully the colors make it easy to see what's going on. These are also wavefronts where every adjacent slit I'm looking at superpositioning with the extra wavefront that we've had, one extra wavelength that we've traveled. Now, I've chosen this diagram badly because I can see that I can only get the 0th order and the first order. I don't think I can get the second order. If I can only just get it. I should have used much smaller wavelengths. But that's what's happening with our diagram. Remember, the ray is always going to be perpendicular to the wavefronts. So the rays are going to be going like this. This is going to be the first order ray. It's going to be going like that because it's going to be perpendicular to the wavefront. Perpendicular to wavefront. So remember, diffraction was the spreading out of the wave, which was caused by the superposition of these wavelets. And it's the same principle that we use, but we offset each time. I don't want to keep explaining it, but we're looking at the for the 0th one there. For the first slit above 0, we are connecting to the first wavelet. Then the second one, we're connecting to the second wavelet. The third one, we're connecting to the third wavelet. That's 3 wavelengths away. The 4th one, we're connecting to the 4th wavelet. That's 4 wavelengths away. The 5th one, we're connecting to the 5th wavelet. That's 5 wavelengths away, and so on. Hopefully that makes you have a better understanding of why this diffraction happens at all, and why we get these orders, these very bright orders. So let's derive an equation then for the diffraction grating. So let's just draw a straight line straight down here, because we've got an idea of what's going on now. For each adjacent slit, we add 1 wavelength of path difference. So we can use that to derive the equation. Derive equation. And let's just do this and say that for each adjacent slit, we add integer. I just put integer. There's no R in the middle of it, is there? Integer number of wavelengths path difference. So we're just going to look at two adjacent slits. Let's have, let's try and draw this. Move up a bit, give me a bit more room then. Right, there's one slit. There is, why do I do that? I keep doing that when I can use the eraser tool. Let's just draw that as my slits. And let's rub out that bit there and that bit there for my two slits. And I've got my 0th order where the rays are going to be parallel. The rays have to be parallel so that our wavefronts are all going to add up nicely. So that's our 0th order. We're not very interested in the 0th order. These are rays, so we should draw arrows on them. This is 0th order. What we're interested in is, let's say, the 1st order. So for the 1st order, we're going to get rays that are still parallel. Make them a bit longer. They're still parallel, like this. And they're parallel because all the wavefronts all add up quite nicely, as you can see from Huygens' diagram on the left. But there is now a path difference. This is going to be the nth order. And let's zoom in like this. I can say that this here is the distance between adjacent slits D, like that. I don't need to use any small angle approximation stuff. I don't have to do that, so I can take my green one like this. I can draw a straight line like this, and as long as it's perpendicular, which is roughly that, then I know that this path difference there is equal to n lambda. If it's 1 lambda, that's the 1st order. 2 lambda is the 2nd order. 3 lambda is the 3rd order, and so on. Now, this angle is this angle here, which we can just call theta. We can just call that angle there theta, the diffraction angle. And now we've got a simple right-angled triangle. So the equation, we just write down the equation. N lambda divided by d is equal to the sine of theta. Sine of theta is equal to the opposite, n lambda divided by the hypotenuse, which is d. And so our equation, it just falls out. N lambda is equal to d sine theta. Remember that with d, we usually get given the diffraction grating spacing in lines or slits per millimeter, so we have to do the reciprocal of it. And so that's d. Remember that n is the order number and theta is the angle, which we'd usually give in degrees. We could give the angle in some sort of interesting unit called arc minutes. An arc minute, let's say 60 arc minutes is equal to 1 degree, and that's going to be 60. That is equal to 60 arc minutes. It's a unit of angle. We could also say arc seconds. We could say that 60 arc seconds is worth 1 arc minute, and so that is 60 arc seconds, because you might be measuring very small angles indeed. I mean, my spectrometer at work has a vernier that can measure arc minutes down to 5 arc minutes, I think it is. So that's useful to know about. I might as well mention it now. Yeah, we can use these diffraction gratings instead of prisms to split colours up, to measure diffraction angles, and then use those diffraction, the angles to those diffraction orders to determine wavelengths, and then use E equals hc over lambda to determine the excitation energies, and it links all the way back to the energy levels we talked about in a previous lesson, where you get spectra, you get line spectra from emission that you can use to determine excitation energies. So types of spectra. I'll say types of spectrum. Types of cat, types of spectrum, types of dog. I'm just thinking it'd be singular there, wouldn't it? Types of spectrum. So what types of spectra are there? Spectra is the plural of spectrum. You can have 3 types of spectra that are interesting. Just to finish off this topic, you can see a spectrum by passing light through a spectrometer which has a diffraction grating in it. The diffraction angle depends on the wavelength, so it produces a spectrum on each order, where with the higher orders we get larger spreads of the different colors. So types of spectrum. We can have a continuous spectrum. Continuous spectrum. This is if you have something like a filament lamp or a white light source. Filament lamp is a good example. Fire, all that sort of thing. We have a line emission spectrum. It's called a line spectrum because we use a single slit and it produces a line to make a coherent source. Line emission spectrum. So this might be, for example, your Geissler tube, your gas discharge lamp. Gas discharge lamp. The Geissler tube, that's not producing monochromatic light. There'll be a bunch of colors depending on the excitation levels in the gas, and it's not producing coherent light, so you have to use a single slit to produce coherent light. That slit gives you a spectrum of lines. The lines are images of that slit. And then we have a line absorption spectrum. And this is the situation where, for example, you might be looking at the light that's passed through a gas, and you might be interested in the composition of that gas. So we could say white light passed through a gas, maybe a hot gas, a glowing gas, something like that, is going to cause the glowing gas to absorb certain colors where excitation can happen. So white light passing through a glowing gas has colors removed. And what will that look like? Well, that will look like a spectrum of colors with dark lines in it, missing colors. It'll look like a continuous spectrum, but with missing colors. I could try and draw sketches of these, but I'm not going to be able to do very well. The continuous spectrum, actually, I think I did before, didn't I? Where was my continuous spectrum? Where did I draw that? Because I could just copy and paste from before. Oh, yes, let's steal that. I don't want the labels, I just want that bit there. Copy, I know what I'm doing, and then paste it down here. How do I paste? We go into there and choose paste. Oh, yes. So there's our continuous spectrum. There's going to be our absorption spectrum, and I'll have to draw an emission spectrum in a minute. So let's just line these up. Oh, this, you can't do that on paper. So that is that one. This is this one. So there's going to be dark lines in amongst the spectrum corresponding to certain colours. Let's try and draw these lines so they go from the top to the bottom. And then lastly, we would have our emission spectrum, which will look very similar. No, don't do that. Copy and paste. Duplicate it. There we go. But what we would have is, choose the rubber, get rid of these highlighted bits here, and then we're going to change the color of these. So that might be, not that one, that one might be red, that one there might be yellow or orange, that one there might be blue, that one there might be purple. Look at that. That is brilliant. So it would be the same gas that causes an emission spectrum that looks like this as causes the absorption spectrum you can see on the bottom. See where the dark lines line up with the light lines. If you get the gas excited, maybe with high potential differences across it, you get it to glow and it will emit certain colours. If you get that glowing gas and you pass white light through it, then it will get an absorption spectrum that looks a bit like what you've got beneath. So they're the same gas. And those are the three types of spectra. I could actually move this around a little bit to make the notes a little bit nicer, rather than having those arrows lining things up. But you know what? I'm going to leave it like that. And how do you get that spectrum? Well, you use your diffraction grating. So you look at this, the first or second or third, never the zeroth order, that would be boring. All the colours of light would be over the top of each other. It would just look white, or if it's monochromatic, it wouldn't be very interesting. But if you used a source, some sort of gas that glowed with a line spectrum like you can see here, then you pass that light through a single slit to produce the line, then pass that through a diffraction grating. Then you look at the first, second, third, or so on order. What you would see is the lines spread out. And then you use your spectrometer, which I think we've talked about before, where you move the telescope around with a crosshair, looking through it, microscope, should I say, looking through the microscope eyepiece with the crosshair, line it up, make measurements of the angle, use those diffraction angles and the order number, which you just count, to determine the wavelength, and use E equals hc over lambda to determine the excitation energy. The last interesting thing you might be asked to do is to calculate what the maximum order might be. So calculating the maximum order, that's CAC, calculating maximum order. Now, how would you calculate the maximum order? The maximum order will be when the diffraction angle is 90 degrees. So you would take, for example, theta is equal to 90 degrees. In the equation, n lambda equals d sine theta. So you plug that in. Sine of 90 is 1. So n would just equal d over lambda. But you choose the highest integer. You don't round up. You choose the highest integer. So if d over lambda is equal to 4.9, the highest order is 4. If d over lambda is equal to 3.2, the highest order is 3. And if the highest order is 3, you're going to get 7 dots, because of what we already looked at earlier on in these notes. And I'm going to stop there. That's the end of optics. Congratulations for getting through lesson 30. We're going to move on next lesson and start looking at forces in equilibrium. That's the next topic, and I hope you'll join me then. Bye-bye.